General lab safety encompasses a comprehensive framework of policies, procedures, and practices aimed at protecting individuals, minimizing accidents, and maintaining a secure working environment. It spans a wide array of considerations, including the safe storage and handling of chemical, biological agents, and radioactive material, as well as the proper use of personal protective equipment (PPE) and adherence to stringent safety protocols. The importance of lab safety cannot be overstated. Beyond safeguarding the health and well-being of laboratory personnel, effective safety measures are crucial for preventing environmental contamination, preserving research integrity, and complying with regulatory requirements. Laboratories that prioritize safety also foster a culture of responsibility and accountability among staff, promoting teamwork and collaboration in the pursuit of scientific excellence.
Hazards from radioactive radiation can occur when radiation from external sources or radioactive materials penetrate into the body. The effects of the radiation depends on three factors: dose, duration of exposure, and working with radioactive materials. The first one is radioactive damage caused by dose. An exceeding certain limit of radiation dose can cause damage when it gets absorbed into our body. Radiation dose is measured in unit sievert. The damage of radioactive hazards may include radiation dermatitis, cataract, organ failure, and radiation sickness. The risk of radioactive damages increases as the radiation doses increase. 6,000 millisieverts may lead to death with acute exposure. 1,000 millisievert exposure in less than 24 hours may cause radiation illness symptoms. 100 millisievert is high penetrated dose for a radiation worker in over 5 years. 4 millisieverts is average annual dose to fins exposed to radiation by different sources. 2 millisieverts is annual dose of cosmic radiation to an aircraft worker. 0.1 millisievert is dose of radiation to a patient having a lung X-ray. Last but not least, 0.01 millisievert is the dose of radiation to a patient having a tooth X-ray. These are the dose limits recommended by International Commission on Radiological Protection (ICRP) 1991. First is occupational exposure. 50 millisieverts maximum in any 1 year, 100 millisieverts in 5 years, and for working figure, 20 millisievert per year. As for public exposure, 5 millisieverts in any consecutive years, and for working figure, 1 millisievert per year. Next is radioactive damage caused by duration of exposure. A longer exposure period may cause induced mutation to human bodies such as cancer. Cancer usually develops years after the exposure to the radiation. Radioactive leaks from a nuclear reactor can cause rise in mutation rates. Rising mutation rates can lead to cancer, birth defects, and hereditary diseases. The basic principle of radioactive protection is ALARA. ALARA stands for exposure as low as reasonably achievable. There are some recommendations by the International Commission of Radiation Protection to limit the exposure. First, to avoid unnecessary personal radiation exposures. Next, keep occupational exposures as low as possible. Last but not least, do not exceed the radiation dose limits. The third one is radioactive damage caused by working with radioactive materials. There are 4 important steps to follow before we start working with radioactive materials. First of all, we need to contact the radiation safety officers to obtain permission to use particular isotopes. Secondly, we need to attend the radiation management meeting. Other than that, we also need to obtain a radiation monitoring badge or personal dosimeters. Last but not least, we need to make sure to work using SOP that has been approved by the Department of Radiation Safety Officer. There are some do's and don'ts while handling radioactive materials. For the do's, we need to keep a safe distance from the radioactive sources. Next, we need to make sure to work with appropriate shielding. Other than that, we also need to wear disposable polyethylene gloves while handling isotopes. For the don't, we cannot go near the radioactive materials without wearing a film badge. Last but not least, we cannot mouth pipette radioactive materials up into the pipette.
Next is General Safety Rule and Glassware Safety. General safety rules have two types, which is the first one is you need to listen or read instructions carefully before attempting to do anything. Second, you need to notify your lecturer if any spills or accident occur. Next, keep hands away from face during lab work, and you need to wear safety goggles to protect your eyes from chemicals, heated materials, or things that might be shattered. Next, you need to wash hands with soap and water, and lastly, tie back long hair and roll up loose sleeves. For general safety rules number 2, you need to know the location of the fire equipment such as fire extinguisher, fire blanket, eye wash station, and first aid kit. Next, you need to wear glasses rather than contact lens. The third one is you need to clean the lab area at the conclusion of the laboratory period. Fourth one is you need to keep the work area uncluttered. Never put anything in mouth during lab experiment. And lastly, never horse around or play practical jokes in the laboratory. Let's move on to glassware safety. The first one is, if a glassware chipped or cracked in the laboratory, you should not be used it. The second one is, broken glassware should not be disposed of in a classroom trash can. You should put it in a special place. The container used for pouring should rest on the table, or at least should have a hands to hold it. Next is a glass stirring rod used to prevent liquid from splattering, and you do not try to clean a broken glassware. You need to tell your teacher. Next, apply a lubricant to the glassware when inserting glass tubing into a rubber stopper. Use a lubricant like glycerin to the glass, and use a twisting motion when you applying it. Lastly, do not place hot glassware in water. It might cause rapid cooling, and it may make it shatter. Now we're going to talk about chemical safety. In order to be safe when handling the chemicals, you need to wear protective goggles and a lab apron whenever you're heating or pouring hazardous chemicals. The second one is never taste any chemicals, and you should not taste anything in the lab. The third one is never pour water into a concentrated acid. Acid should be poured slowly into water. The fourth one is never mix chemicals together unless you're told to do so. Next, whenever you need to smell something, just waft the fumes toward nose with one hand to smell the odor. You do not put your nose over the container and inhale the fumes. Next, follow the instructions of the teacher. And lastly, wash hands after handling hazardous chemicals. Now here we are to the last thing that I'm going to talk about, which is specific precautions for handling acids and bases. When you're handling an acid, you always need to add acid to water, never water to acid. This is to prevent exothermic reactions that can cause splattering and thermal burns. Next, pour acid slowly into water while stirring continuously to dissipate the heat generated. Or else you can use fume hoods in order to handle volatile or harmful chemicals like concentrated acids and bases in a fume hood. This is to avoid inhalation of harmful vapors. Next, you need to proper ventilation and regularly check that the fume hood is functioning correctly.
Electrical safety. Lay electrical cords where no one can trip on them or get caught in them. Be sure your hands and your lap area are dry before using electrical equipment. Never poke anything into electrical outlets. Unplug cords by pulling the plug and not the cord. Unplug all electrical equipment at the end of the lab period. Heating safety. Let burners and hot plates cool down before touching them. Use tongs or protective gloves to handle hot objects. Never reach across an open flame or burner. The only type of glassware that may safely be heated is either Chemex or Pyrex. Always point the top ends of the test tube that are being heated away from people. When heating a test tube, move it around slowly over the flame to distribute the heat evenly. Only glassware that is truly dry should be heated. Heat glassware by placing it on a wire gauze platform on a ring stand. Never leave a burner or hot plate unattended.
The first one, we go to how to handle the microscope. The first step is we should place one hand under the base of the microscope. This provides stability and prevents the microscope from tipping over. With the other hand, grabs the arm or the frame of the microscope. The arm is typically located above the stage and housed or focusing knobs. Next, we must carry the microscope close to the body to maintain balance and control. Avoid swinging or twisting movement that could damage internal components. When we want to place the microscope back on a surface, ensure it is placed on a stable, flat area. Avoid uneven or unstable surface that could cause the microscope to wobble or tip over. The most important thing is we must avoid touching the lens with our finger because the oil from our skin can damage the lens of the microscope. Next, we go to how to use the microscope. The first step is we must adjust the interpupillary distance, which is the distance between the eyepiece to match with eye spacing. Once the specimen is fully focused, use the fine focus knob, which is the smaller knob, to make small adjustment for the sharper image. This knob is used with higher power objective lens, so we can observe the specimen through the eyepiece. Adjust the focus as needed to examine different parts of the specimen. The last one is we should turn off the microscope and unplug it if necessary. We can store the microscope in a clean, dry environment. We should cover it with a dust cover or store it in a case to protect it from the dust and damage. Okay, next we go to how to clean the microscope. The way to clean the microscope is divided into two parts, which is the optical part and a frame and stage part. For the optical part, we must use a blower bulb or compressed air to gently blow away loose dust particles from the objective lens and eyepiece. Use lens paper to gently wipe the objective lens in circular motion from the center outward. Avoid applying excessive pressure. If there are any stubborn smudge or fingerprints, moisten the lens paper with a small amount of lens cleansing solution or dilute isopropyl alcohol. The next part, which is the frame and stage part, we must ensure the microscope is turned off and unplugged. We need to use a soft, lint-free cloth or lens paper lightly dampened with a mild soap solution or optical cleaning solution, diluted if necessary. We need to gently wipe the frame, stage and mechanical part to remove the fingerprint, oil and any visible debris. Avoid excessive moisture and ensure the cloth is only slightly damp to prevent water damage.
These are the examples of real-world implementations. First, in Oak Ridge National Laboratory in USA, there is an implementation of advanced containment and ventilation technologies in labs handling high-activity radioactive materials. Meanwhile, in the European Organization for Nuclear Research (CERN) in Switzerland, there is a comprehensive radiation protection procedures are in place, such as shielding, access restrictions, and continual monitoring in order to ensure the safety of personnel working with particle accelerators.
Benefit in general lab safety. Prevention of accidents encourages safe behaviors that lessen the possibility of spills, fires, and other accidents that could cause harm or damage. Enhance productivity. A safe lab environment fosters productivity by reducing downtime due to accidents or safety incidents. Protections of personnel ensures the physical well-being of lab workers by minimizing risk of accidents, chemical exposures, and injuries. Challenges in general lab safety. First one is managing hazardous materials. Hazardous material and trash handling and disposal requires certain expertise and infrastructure. Next is complexity of regulations. Keeping up with evolving safety regulations can be challenging, especially in multinational or multidisciplinary labs. The last one, the challenges might be from human error. Despite regulations and training, human error can sometimes result in safety breaches. Regular monitoring and reinforcement of safety practices are required to reduce this danger.
The next one is future and innovation. The first one is virtual and augmented reality, which is VR and AR. VR/AR simulation is to train lab personnel in handling emergencies, operating equipment safely, and recognizing potential hazards. Next is smart personal protective equipment. Integration of sensors into PPE such as gloves, goggles, and suits to monitor environmental conditions such as temperature, chemical exposure level, and alert wearers to potential hazards in real time. Development of wearable devices that can track physiological parameters of lab workers, such as heart rates and respiratory rate, to ensure their health and safety. The last one is automation and robotics. Increases use of automation and robotics to handle hazardous material and perform high-risk tasks, reducing human exposure to dangerous substances.
In conclusion, general lab safety is crucial because it protects both individuals and the environment from potential hazards inherent in laboratory work. Adhering to safety protocols minimizes the risk of accidents, chemical exposure, fires, and other emergencies that can cause injury, illness, or damage. It ensures that experiments are conducted responsibly and effectively, promoting a safe working environment for everyone involved. Compliance with safety measures also maintains regulatory standards and promotes good scientific practice, contributing to the overall integrity and success of laboratory research and operations.